Today we're going to start looking at Chapter 1, Functions. This is kind of a review of previous math, so depending on your math background, you may or may not be more familiar with the math that we're doing. We're going to go back to just reviewing functions themselves, kind of taking things back to basics. One of the things we hear a lot with functions is the idea of input and an output. So what we're inputting is always our x value, which we also consider our independent variable. Once we take that x value and we input it into our function by replacing x with the value, we get an output. So think about this like a calculator. You're inputting something into the calculator. Your answer you get out is your output, which we call f of x, which is also known as the y value. So there's this nice input-output relationship. The domain are the values that we input into the function, and the range is the values that become the output of the function. Now, to be a function, we need to have a unique value in the range for the domain values. We can't have them going to the same value. So a function is a rule that assigns to each value x in a set a unique value for f of x, meaning y value. So we want to start associating that f of x with y. The d or the x value is going to be the domain, and the range is going to be f of x, which we also know we call that the y value as it varies over the domain. So if an x value is not in the domain, the correlating y value is not in the range. So if plugging in x gives you something that might be undefined, that would tell you would not have a range value there. The quickest way to tell if something is a function is, of course, the vertical line test. So Desmos is a great place to go in and input your function or equation into Desmos and then quickly see if it passes. If you draw a vertical line and it touches twice, it fails the test and it's not a function. But in the graph on the right, if I draw the vertical lines and it touches only one time, that is considered a function. So this is a great quick way to see what happens. And you can also see here that there are two y values for this x value, which is why it touches twice. So sometimes it's a little hard to visualize what's going on there, but that's definitely the relationship. And so, as we said, the vertical line test is what we do to test to see if something is a function. And you should be able to draw multiple vertical lines on the graph to see if it touches once or twice. So here's an example. If I draw vertical lines along this graph, it will only touch at one point per vertical line. So this would be considered a function. In this equation, the circle, every vertical line that I draw will touch more than one time. Therefore, this is not a function. So very quick way to test this. I know this one can be a little tricky because you see kind of this flat area here, but if we're drawing vertical lines, and don't be afraid to put your finger on the computer screen, if you're drawing those vertical lines, you're going to see that this is also a function. Now here, again, right off the bat, I can look at the axis, and the axis crosses this graph twice, so this is not a function. And so when we start looking at the idea of domain and range, the way I like to explain it is our domain is from the left to the right. So all of the x values that exist along the graph from the left to the right. So with this parabola, we should typically draw arrows here. And what those arrows indicate is that it gets wider and continues going up on both sides. So if I'm going left to right, the domain is going to be negative infinity to positive infinity, because as that gets wider, there will be an x value on the graph as that parabola continues to grow. The range we look at bottom to top. So if I start at the bottom, the graph doesn't start on the y-axis to this point, and then it will continue to grow and go up. So my range would be 1 to infinity. And that would include the 1 value, so I would utilize a bracket, or we could also use the inequality notation. Here with this circle, a circle doesn't go on forever. So I know that from the equation that I'm given. So this is a limited domain. So I go from the left, the graph starts at -2, and it stops at 2. So my domain is -2 to 2, brackets because we're inclusive. Range is bottom to top, so I will start here at 0, and it will go up to 2. So think left to right, bottom to top. And I've included a couple of examples here that you can also look at. Composite functions are another idea in this unit that might be something you have previous experience with, depending on your math background. What I like to say is composite functions are like nesting dolls. So it's something inside of something else. So when you see this notation with the open circle, that's pronounced f of g of x. And if you notice, I've taken g of x and I've put it inside of that parentheses, like a nesting doll. If you're not familiar with nesting dolls, you can Google those really quick on your computer. They are the dolls that are made with one doll inside of another. So what we're doing here is we are replacing the x value in some equation with an entire other equation. So if I have two separate equations, f of x and g of x, I could plot them on the same graph. And then I can look at a couple of things here. I can look at what I'm most interested in with calculus is I'm interested in this little segment. This should look familiar, right? This little segment would be my slope. So it's how much it's changing. And I'm looking at this curve here. But what happens is we're not able to calculate the slope of a curve. We haven't learned that from our algebra background. So what I've done is I've taken this line and drawn it through. I have this secant line. And if I can find the slope of this secant line, then I'm able to say, okay, this is an approximation for the curve. So even though I can't actually find the slope of a curved thing, I know from algebra that I can do y2 minus y1 over x2 minus x1, and I can get the slope of that secant line. And so what I'm seeing here is my y value, my change in y, would be f of x plus h minus f of x. That would be how much it goes up. And then my run would be h, which is where this formula is coming from at the bottom of your screen. And then here we have a simpler approximation. It's the same thing. I'm using slope, but now I'm starting to look a little more like that formula from algebra, where f of x is y, f of a would be the point up there, up down here. So I have y2 minus y1 over x2 minus x1. So we're getting used to seeing some different letters in the game, but we're really just finding the slope. That's all you're doing is just finding the slope. The notation just looks a little wonky. So if I'm here on this graph, to approximate the slope of my curve, I'm going to actually take the slope between these 2 points, and I'm going to do y2 minus y1 over x2 minus x1, and I can approximate that slope. Now, what happens here is that's going to be kind of a nasty slope because I'm going to have 1 over 9 pi minus 1 over 4 pi over 15 minus 10. So we are going to have to deal with that fraction. So when you do that, make sure that you are dealing with the fraction in the numerator and simplifying it fully. That's why the pi goes in the bottom here. So once we start getting into these graphs and these secant lines, we have symmetry. We've talked about symmetry in algebra, but again, it might be a while since you've seen algebra. So something is symmetric to the y-axis. That would be like a parabola. So think about a parabola. If you fold the paper on the y-axis, the parabola is on top of itself. If it's symmetric to the x-axis, that could be something like a sideways parabola, where if you made the fold on the x-axis, it would be symmetric. So what we say is that if I plug in a positive x and a negative x, I'm going to get the same value. And you think about a parabola, when you have x is positive 2 and x is negative 2, it has the same y value. And then here, if I plug in the same x, I'm going to get a positive y and a negative y out. Those are kind of difficult to think of right now because we don't have a lot of experience with those. So it's okay if it's not quite, you're not quite able to figure out an equation that goes with that. And something is symmetric about the origin if I can plug in x, y, and get the negative x and negative y out. Something like that could be where you're making multiple folds. So maybe a well-placed circle could do it, or maybe perhaps a line about y equals x. So there's a couple different ways. We don't see a lot of symmetry about the origin with natural functions. You might see some that are drawn in the textbook that are going to be a little more clear. So here's some images with symmetry around the y-axis, like I said, a parabola. Symmetry around the x-axis, like I said, a sideways parabola. And this would be something symmetric about the origin. If I folded it over the y-axis, it would kind of reflect this, right? And then if I folded it over the x-axis one more time, it would lie directly on this line. So you can take a moment and sketch that on a sheet of paper, and you can see how when you make those folds, it is going to wind up on top of itself. So the symmetry does happen by looking at the points and checking out the point values. Is there a point x, y, where on the graph there's also a negative x and negative y value? So if this was 2, 1, this should be -2, -1. That's one of the ways we can check for symmetry. If this is 2, 1, this should be 2, -1. So we can kind of quickly look at a graph. It's much easier to see symmetry about the x and the y-axis than it is about the origin. And so we start to give them names. An even function has the property that if I plug in a negative x value, I'm going to get the same y value out for it. And that's why, because it's symmetric about the y-axis. An odd function happens where if I plug in a negative x value, I get the negative of the y value out. That's also symmetric about the origin. So it's really much easier to see an even function than it is to see an odd function, just because the nature of how the odd function would be symmetric about the origin, which does require those two folds. So if I'm looking here, this would be considered an even function because if I fold it across the y-axis, it is even. This one has no symmetry. It's not even or odd because if I fold this over the y-axis, I just get this weird function here. It's not symmetric. And I fold it across the y and then the x, I'm going to get this opposite motion. It's not going to be directly on top of itself. And you can draw it out on a sheet of paper and make those folds yourself just to see how they behave. This would be an example of an odd function because if I fold this over the axis and then over again, it would wind up on top of each other. You could also check those points like it's showing you here, x, y, -x, -y, to make sure if I have 1.5 and 1.053, I do have the negatives there. If I have this, I do have the opposite symbols there. So you can use the points or you can use the fold method, whatever you're more comfortable with. And that is 1.1 in a nutshell. I know that was a very quick algebra recap, but 1.1 does have the most information as far as that goes with things you're reviewing from previous information. We have a grouping of what we call functions here. We have algebraic functions and we group them into rational and polynomials. Then we have transcendental functions that give us that nice curvature, trigonometric, exponential, logarithmic, and there's a lot of different ones that we consider transcendental. So putting them in these two different categories will help you keep them a little bit more straight as we start learning strategies to deal with them. And if we look here, I've got a snapshot of a wave, and I also have this other graph. So based on what you've learned in the text, what do you think would be a transcendental and what do you think would be an algebraic function? So take a minute just to kind of think on that and think about which one meets those qualifications. Here I have a line which is going to fall into that algebraic symmetry. I have a y-intercept and I have another point. So there are several things I can calculate from this. I can find the slope of this because I learned that in algebra. It's not curved, so we can just use the y2 minus y1 over x2 minus x1. That's a great thing that we can do because lines follow that formula. Curves do not, which is why in 1.1 we talked about the secant line by using that straight line to approximate the curve. Here's another example of a straight function. Even though I'm not given these exact points, I can estimate these points to find the slope, or I can look at the function itself to find the slope that's here. So this would be a graph that I can find the slope of using the information I've learned in my algebra class. This is a piecewise function, so I find a lot of students don't have a lot of experience with a piecewise function. So there's a couple things I want to point out about this function. If you see these open circles, that means the y values at those points are not included. So if I asked you for the f of 2 or the y value at x equals 2, that answer would actually be 3 because this dot is colored in. So with piecewise functions, we have jumps here, and so because at this moment I pick my pencil up, this would not necessarily fall under a continuous function. So it wouldn't necessarily be continuous, but I do only have one y value here, which is why I'm using the terminology piecewise function. And then the same thing applies here. I have a piecewise function. This is what it looks like algebraically. And if you notice, I have this hole here, which we call a removable. So if I'm looking for the f of 2 or the y value, that is going to be 1. So it's not going to be down here. It's going to be 1 because we're colored in here and we exist. So you want to keep this in mind as you're looking at these functions and you're starting to see them look different than what you saw in your algebra class. And there's a reason for this, and as we move forward in week 2, this is starting to become clear. But I just want you to start looking at these functions, identifying the y value, and asking yourself if it's continuous. Here's the graph of y equals absolute value of x. We want to refamiliarize ourselves with all of these graphs that we've learned in our algebra classes. And so I've kind of included several in these slides just to make sure we're going through and remembering. So here's x squared, x to the fourth, and x to the sixth. These are kind of what we call in behavior models. So keeping those in mind or on a note card is going to be extremely helpful as you start to look at the equations in these sections and think, what does that actually look like? A lot of what we're going to do in calculus is going to be based on what these functions actually look like. So we're going to need to know, hey, if I see the equation square root of x, that responds to this graph, because a lot of the things we do in calculus will be related to the graphical representation of it. So there's just a couple more of these behavior graphs. And then we have some terminology. So we have peaks and valleys. That should make sense. Peak is a high point, valley is a low point. Those might be terms that you haven't used in the past, but we're going to kind of use those terms as we approach this calculus course. So peaks and valleys, kind of related to something I'm pretty sure most of you guys can get the drift of what it is. Now, tables, where do these tables come from? So from algebra, we did table of values before we really knew what to graph. So on the left-hand side are the values we plug into the function. On the right-hand side are the values we get out of the function. So this would be considered my x, and this could be considered my y. So I'm replacing and I'm getting these values out. Table of values are used in calculus because we can use them to approximate a secant line. So they are very helpful, just differently helpful than they were in your algebra course. So using those table of values, I can plot points, and then I can make some assumptions. This doesn't appear to be a straight line. Do you see that? If I connect the dots, I can probably connect the first and the last one pretty straight, but there's a definite curvature to what's happening here. So again, my algebra definition of slope doesn't quite apply here, but I could approximate the slope by sketching in a secant line and trying to estimate the slope of this curved pattern. And so here's where I connected the dots, what it would look like. I notice again, there's a slight curvature here, which just tells me again that I am working with a curved function. Now, what does this function remind us of? Well, if we follow this function, it's increasing. We're going to use that word increasing a lot. Increasing means it's going up. But what happens here? It's flat. When it's flat, we say it's constant because the y value is 2 for this entire interval. Then it goes down, so we say that it is decreasing. This is going to be a really important function within calculus. When you start seeing graphs, I want you to start recognizing where is it increasing, where is it constant, where is it decreasing. As we move through the middle weeks of this course, we're going to start talking about why that's important. So right now I'm just planting the seeds in your mind so that you're recognizing what is important and what we'll be carrying with us. Because sometimes I know that it's hard to see where we're headed, but we do want to build upon these concepts. And again, here's a piecewise function. It's flat, so it's constant. It's constant, it's constant. So nowhere on this graph is it increasing or decreasing. If I want to know the y value for x equals 1, look at this. All these circles are open. So there is no y value here because the circles are open. Also notice over here, I don't have an equal to anywhere in this equation. So it's not going to be able to be considered that we have a y value there at 1 or at 2 because it doesn't equal any specific value there. Here I look at this function and it's increasing and then it's going constant. So I'm putting this together by graphing the graph of y equals 2t between 0 and 3. So there's my little y equals 2t. And then doing 6. So notice how we get that constant is we have a constant value. So it's going to be 6 if t is greater than 3, which means I'm just graphing the y value of 6, constant, straight line. Now that I'm looking at these constant curves, I can start to calculate area. Again, going to be important later on in the course. So if I'm looking at these grids, if I'm looking at the area, look at this. They divided this into a right triangle. And I know the area of a right triangle is 1/2 the base times the height. So I could find the area under this graph. And you're probably thinking, why would I want to do that? It's going to be important later. Hold it in the back of your mind. Here, I could divide this into a rectangle. So I'd have this rectangle right here. And I would have this triangle. And I could add the area of those two figures together to find the area of 5. So this is a of 5, which means from 0 to 5, the area under the whole piece. I could divide it into two shapes. Again, here's another area figure. I'm trying to work with shapes that I know because I can find the area of shapes that I know. Here's another example of a graph. What is it doing? It's y equals x squared between 0 and 3. And then it's going to be 6x minus 9 if it's greater than 3, which is why we kind of get this straight. Notice how it goes from being curved to straight. That's because I'm graphing these two together. And if I plug in 3, 3 squared is 9. So up here, if you look at that point, that looks to be roughly 3, 9. If I plug in 3 here, I'm going to get 6 times 3, which is 18, minus 9, which also happens to be 9. So that's why we don't have any interruption in this graph, and it really does just kind of look like a parabola. It would really take seeing this equation here to know that it's not just a parabola. As we know from our algebra classes, we can start shifting, stretching, and shrinking these functions. If I do it on the outside, it drops it down 2. If I add it on the outside, it brings it up 3. So that comes back from our algebra. We're moving it up and down based on what we're adding or subtracting to f of x. Now keep in mind, f of x is the entire equation or the y value. Here, notice it's done inside the parentheses. When I add or subtract inside the parentheses, it moves it left or right. So if I add 3, it actually moves it left 3. So look here, 1, 2, 3. There's the red graph. If I look here, x minus 2, it's actually going to move it plus 2. There's my blue graph. So I took this dot on the black, I moved it to the right 2. And that's probably one of the easiest places to get confused because we are moving left or right in opposite motions. And so here we're looking at, we're scaling verticals by we're affecting how fat or skinny they are. So we're doing that multiplication, so we're stretching and shrinking the graph. If I multiply my original graph by 2, I'm getting this here. If I multiply it by 1/3, I'm seeing this wider value here. So it's going to be broadened if the value is between 0 and 1. What does that mean? It means a fraction. If you have a fraction between 0 and 1, it's going to get broader. If you have something greater than 1, it's going to be that thinner graph because it's going to be steeper. So that's really all this section is about stretching, shrinking, moving things around, that basic value of the graph and what we're doing to recognize it. So here I've multiplied by 2, which means I've taken it and I've made it that skinny looking graph. If I multiplied it by a fraction, that's what would generalize the wider blue function. So all these graphs, you can kind of look through these slides as you go with them and see what's happening. Again, as I multiply by 2, it's going to be thinner. If I add 1 inside, I'm going to shift it to the left one because it's going to go opposite. So this is just kind of some examples of how the graph is a function affecting things. Now this is a summary. This is in your textbook. So this is a great thing to copy down onto 4 different note cards. It does go over exactly what I just said and how the transformations do come about. So this is 1.3, and I'm going to go ahead and stop the video here, and that way it's a little bit for you to digest, and we'll come back and learn some more in the next video.